Chapter 4 and 5, Displaying and Describing Numerical Data, Video 2. In the last lesson, we learned that to describe a distribution, you should address shape, center, spread, and unusual values. We also learned how to describe shape, but not much about center or spread. In this lesson, we will learn numerical ways to describe center and spread. First, we need to know what a median is. The median of a data set is the middle value. That is, it divides the data set in half. To find the median, we have to put the data in order. I have already put this data in order right here for this example. Now it says, find the value of n plus 1 divided by 2. So we'll do that. Well, n, there are 1, 2, 3, 4, 5, 6, 7 numbers. So n is 7. N is the number of numbers. So 7 plus 1 divided by 2, that's 8 divided by 2, or 4. Now it says, if n is odd, the median will be n plus 1 divided by 2 value in the ordered list. It just means that the median will be the fourth number, or 13, and I'm sure you all could see that that was the middle value to begin with. If we had this next set of data, first off we'd put it in order. Now we need to find the value n plus 1 over 2, and we could do that again and we would get, let's see, n is 1, 2, 3, 4, 5, 6. So 6 plus 1 over 2, that's 7 over 2, it's 3.5. So it's going to be the third number and a half. Well, 1, 2, 3 and a half, that's where our median is. But we want a number for that, so we're going to just go ahead and take the average of those two observations. 17 plus 19 divided by 2 equals 18. So the middle number, or the average of 17 and 19, is 18. Even though 18 is not in our data set, that's still our median. Definition. A resistant measure of spread is a measure that is not affected by outliers or skewness. In the previous example, what would happen to the median if 39 was changed to 399 or 399? Okay, let's change it. Although this is 399, the middle value is still 18. So the median is a resistant measure of spread. Definition. The range of a data set is the difference between the maximum and minimum values. The max value in this case would be 25, the min value 12. 25 minus 12 then is 13. Note, the range is one number, not two. The range is 13, not 25 to 12. Is the range a resistant measure of spread? Not usually. Think, when we change the maximum value here, the range before would have been 39 minus 5, a fairly small number, while now it's 399 minus 5, a much, much larger number. A more resistant measure of spread is called the interquartile range. The IQR measures the range of the middle half of the data instead of the entire data set, which means that the outlier should have no effect on the IQR. To find the middle half of the data, we must identify the quartiles. And the quartiles are the numbers that break the data into equal fourths. I'll let you go ahead and read all of these steps and definitions, but let's just break the data up. And then we'll use it to find the median, the quartiles, and we can also find the range and the interquartile range. Here's some data in a stem and leaf plot of test scores. Okay, if you counted up all the data, you could go 1, 2, 3, 4. Basically, you'd find that the middle value was 76, but it's hard to do on a stem and leaf plot. So I've organized the data, and then if I count it, I would find the middle value is 76. Well, that's quartile 2, because it breaks it in half. It's also the median. Now, I could break this data in half, and if I counted 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, half of that is 7. 1, 2, 3, 4, 5, 6, 7. So the number right here would give me 7 data points here and 7 here, which means my Q1 must be the average of 65 and 66, or the number right in between, 65.5. Similarly, I would do the same thing over here, and I would get 88. Notice the average number between 88 and 88 is 88, and this would be Q3. Lastly, you could see that my min is 12 and my max is 100. This leads us to the 5-number summary of a distribution. It's a list of the min, Q1, median, Q3, and max. The 5 numbers we just found are our 5-number summary, so 12, quartile 1, median, quartile 3, max. And I'm going to use them to build a box plot, which is a graphical display for the 5-number summary. So notice here that I have a scale. I'm going to plot these numbers. So I've got 12. I also have 65 and a half, 76, 88, and 100. And I make a box around the middle 50% and connect to the min and the max with the line. This is a box plot. What's interesting about a box plot is this is the interquartile range, the middle 50% of the data. And again, this is the min, Q1, the median or Q2, it's the same thing, Q3, and the max. And it shows us that the data is skewed. Okay, you can see the data is left skewed. There's another type of box plot called a modified box plot, and this is useful because it shows the outliers. We mark them as a dot. However, we need to determine if something is an outlier, so we have a formula for that. To determine if something is a low outlier, we do Q1 minus 1.5 times the IQR, which means we go from Q1 and then we say 1.5 times this, so this much this way, plus a half more. We say anything less than that is going to be an outlier. And we do the same thing the other direction to find the upper value. And if we do that mathematically, we need to know what the IQR is. Well, the IQR is from here to here. Well, Q3 was 88 minus Q1, which is 65.5. So the IQR is 22.5. So we'll put that in the formula. And you can see that the cutoff for a lower outlier is 31.75. So anything lower than 31.75, and my estimate was close, anything over here is going to be an outlier. Turns out we have one number over there, and that's 12. Let's look up above, put it in the formula. Anything bigger than 121.75 would be an upper outlier. Well, our data only goes to 100, so we don't have an upper outlier, but we could redraw our box plot, and we move our minimum number now to the next number in front of the lower fence, which is 37. So about here. And this becomes our new box plot. And I actually prefer these because it tells you a little bit more information. We're going to talk about comparing distributions again. Whenever you are asked to compare distributions, you must compare shape, center, spread, and unusual values, and do it in the context of the problem. To compare, you should use phrases like, the male distribution has a higher center and is more spread out than the female distribution. Here we have two classes, period 2 and period 4, and their test scores. And let's go ahead and compare them. First, we're going to talk about shape. Notice I say something like period 2 has test scores that are symmetric, while period 4 has left skewed test scores. I list both periods and compare them while describing. Now let's talk about center and spread. First off, we need to look at the median, or the middle number. Well, period 2 we said was kind of symmetric, so the median is going to be right about here, where with period 4 being left skewed, more of the data is right here, so the middle of the data is going to be maybe right here. So if we were to talk about it, we would say period 2 has a lower median, but it has a larger range than period 4. And remember, range is from the small number to the max, so it's more spread out. Finally, if we look at the unusual values, period 4 may have one or two outliers. Maybe that's an outlier, we don't know, while period 2 does not appear to. Box plots are nice because those things we were just looking at are very easily identified. Please go ahead and fill this in with some comparison sentences of your own. Lastly, let's talk about time plots. Time plots are useful to plot data over time so we can notice trends. trends. For example, considering the following data for the death rates at 2 hospitals. We have Hospital A and Hospital B, and their death rates over 10 months. It says make a dot plot for each hospital so we can see what's going on and see if we can decide which hospital seems to be a better hospital. So for Hospital A, in month 1 or January, they had 7 deaths. In month 2 or February, they had 6. In month 3, they had 5. In month 4, they had 5. Go ahead and fill in, pause the video and fill in both dot plots. If you do that, I think you'll notice it appears, if I ask which hospital is better, that they're the same. They have the same distribution of death. However, now let's make a time plot. A time plot, I've got the months or the time in chronological order on the horizontal axis, and then vertical, I'll list the number of deaths. So for month 1, Hospital A had 7 deaths. Month 2, Hospital A had 6 deaths. Go ahead and plot all those data points for both hospitals, and then we can look at it. I went ahead and did that. Notice I also labeled my axes and my graph itself, my time plot itself, because without labels it's useless. And you can see that in Hospital A, they seem to be doing better as the months go on. Less people are dying in their hospital. While in Hospital B, although they've had some variation, more people are dying. So what information does the time plot tell you that the dot plot didn't? The change in death rate over time. Note, time plots are not appropriate for some data, such as graphing the heights of this class, because you're not going to grow that much over the year. However, a time plot would be nice for graphing the change in heights for one student over time,